And so I've drawn this specifically so that this arrow goes through these molecules. So these greenhouse gas molecules, what that's supposed to represent is that the molecules are not interacting with the solar radiation. So it's just coming in, the light from the sun is just coming in directly. And you can think of this intuitively that our atmosphere has these molecules in it, has CO2, has methane, has water vapor in it, even on a clear day. And if you're out on a clear day and you're looking, at the sky or looking at the sun, don't look directly at the sun, but if you did look at the sun, you would just see the sun directly. It's not obscured by these gases. So anything that's going to be interacting with light is going to obscure the sun. You would have haze or something like that. So these things don't interact with the light coming in from the sun. Something that does would be clouds, right? So if you have a cloud in between your eyes and the sun, then you're not going to be able to see the sun. And that's telling you that the cloud is interacting with the light from the sun and is reflecting light back to space so that it can't get to your eyes down here. And ice on the surface of the planet reflects light back to space. Albedo, how much of the light from the sun is reflected back to space. So about a third of what's coming in gets reflected back to space right away. And so you can kind of see what the major albedo sources are by thinking about looking at the Earth from space, because your eyes can see light. So anything that you can see, if you're looking at the Earth from space, is going to be light reflected back towards your eyes. And the more of that light you can see, the more that light is being reflected back towards your eyes. So something that's dark, that would be something that's going to be absorbing solar radiation, and something that's light is going to be something that's reflecting the light coming from the sun. So clouds are a big reflector of the sunlight. Light deserts are a big reflector of sunlight. Rainforests, jungles are dark, so they are not reflecting much sunlight back to space. Oceans tend to be dark, so they are not reflecting much sunlight back to space. So that's just a easy shortcut to think about what is most reflective, is just think about your eyes looking at the Earth from space. What's coming in, I've been calling it light. I've also been using this term radiation. These are at least three different terms that you'll see in readings or articles. So light is one, so that refers to just the light coming from the sun. Insolation is another one. That's different than insolation with a U. So insolation is the pink stuff in your walls, but insolation is a portmanteau of incoming solar radiation. And then shortwave radiation is the nomenclature that all mostly use in this class, shortwave radiation. And so then what's coming from the Earth, you'll often hear called heat radiation or infrared radiation or long wave radiation. So we see here this kind of dichotomy that we have long wave radiation coming from the Earth and shortwave radiation coming from the sun. We're defining radiation by its wavelength. And so you can see that in this word here, right? Wave, long wave. So it has a long wavelength, short wavelength. Okay, so this is an interesting question though. Why does the Earth give off longer radiation than the sun? This seems kind of bizarre. Like these are both just objects in space, and we're just kind of saying that the sun gives off shortwave radiation and the Earth gives off long wave radiation. Why is that the case? So I'll come back to this in more detail, but it has to do with two laws in physics, and those laws are Stefan Boltzmann's law and Wien's law. And it's Wien's law that ends up being particularly important. But first I'll just tell you what these are. So Stefan Boltzmann's law says that warmer objects emit more radiation or energy than cold objects. So that's pretty intuitive, right? If something's warmer, it's going to be giving off more radiation, more of this electromagnetic radiation than a cold object. And so you can think of that as just like a fire. Like if you're sitting at a bonfire and you feel that heat coming off the fire, you are feeling radiation. You're feeling electromagnetic radiation coming from the fire and like hitting your face. It's not just that the fire is warming up the air and then the air is touching your face, because you would feel that even if there was a vacuum, even if there was no air between you and the fire. So warmer things emit more radiation, and you can feel that. So you can get an intuitive sense for that. Wien's law is what becomes very important for the greenhouse effect and for answering this question, and that is that warm objects emit a higher proportion of their radiation at shorter wavelengths than cold objects do. And so this picture that I have here demonstrates this. So if you turn on a stove, it demonstrates both Stefan Boltzmann's law and Wien's law. And so the Stefan Boltzmann's law part is the same idea as the fire, that when I go from this side to this side, if I turn it on, it's going to be emitting more radiation, and so I could feel that. If I put my hand above it, I could feel that radiation coming off of that stove. And again, it's not just because it's warming up the air and then the air is touching my hand. It would be the case even if there wasn't air there. So that's the Stefan Boltzmann's law part. But the other important thing here is that you can see it change color. What is going on with that? So we have to kind of think about these radiation wavelength diagrams that you'll see, in chemistry and physics type classes. And so what this is showing is our different wavelengths of radiation. So we have longer wavelength over here, and we have shorter wavelength over here. And it's showing that all of these kinds of electromagnetic radiation that we hear about, radio waves, microwaves, infrared radiation, visible radiation or light, ultraviolet rays, X-rays, gamma rays, they're all the same thing. They're all electromagnetic radiation. They just have different wavelengths, and these are shown by this these examples of things that are roughly the same size as that wavelength. So it goes from very big to very, very small. And this is what's important down here for the greenhouse effect, is the temperature of objects at which this radiation is the most intense wavelength emitted. So it's saying that object at a given temperature will emit radiation at a given wavelength. And you see that it goes from cold over here to warm over here. And so that is saying that as an object warms up, it emits more radiation at short wavelengths. So wavelength would be like the crest to crest distance here. And in science books, that usually gets represented with this Greek letter lambda. But yeah, as objects become warmer, they emit more radiation at shorter wavelengths. So what's going on with that stove? There's our visible light. So remember that visible light and different colors are also just different wavelengths of radiation. So our brains label different wavelengths of radiation with colors. So you may remember Roy G. Biv from chemistry or physics class. And those are just the different colors of the spectrum corresponding to different wavelengths. But okay, so going back to the stove. When the stove is turned off, it's colder. It's cold enough such that we can't see the wavelengths. We can't see any radiation coming off of it because our eyes can only see in this very specific band of electromagnetic radiation. So it's cold, it's too cold for us to see. And then as it warms up, Wien's law says that as the object warms up and it starts emitting more radiation, more of that radiation is emitted at shorter wavelengths. And so now there's enough radiation being emitted at short enough wavelengths that we can start to see it. And we see the specific color that is the longest wavelength that we can see. So it's red. So if we go back to the diagram here, we can see red first because some of the radiation that it's emitting we can see, and the first thing that we can see is red. So it's just kind of inching into that portion of the electromagnetic spectrum that we can see. And so why is that important for the Earth-Sun thing? Well, the sun is very hot, and so it's emitting radiation right in the center of the visible spectrum. So that's why we say we can see light, and all that's saying is that we can see the electromagnetic radiation coming from the sun. And it's no coincidence that our eyes are tuned to see the electromagnetic radiation coming from the sun. It's because we evolved on Earth where we are bombarded with this electromagnetic radiation coming from the sun, and so we're using that to navigate our environment. So our eyes evolved in that environment, and so that's why they're tuned to see that. But the Earth is colder. So the Earth is colder than the sun. It's over here. And so the Earth is emitting electromagnetic radiation. It's just subvisible. It's too long for us to see. So it's basically, this is supposed to be kind of a simplifying idea that everything is emitting electromagnetic radiation. The sun is emitting electromagnetic radiation. The Earth is emitting electromagnetic radiation. You are emitting electromagnetic radiation. I am. The only difference between the Earth and the sun is just the wavelength. And the wavelength depends on the temperature of the object. And so the sun is hotter, and so it emits at shorter wavelengths that our eyes can see.